All right, ladies and gentlemen, today's class recording has started. So, on Friday, we introduced the concept, or we introduced the topic of stoichiometry. And like the subheading here says, stoichiometry, mass and quantity relationships among the reactants and products in a chemical reaction. So, stoichiometry allows us to calculate quantities of the substances that are involved in a chemical reaction. Instead of just identifying what the reactants are and what the products are, we can talk about how much of those reactants and how much of those products we make. It's kind of like a recipe, right? We talked about the idea that the reactants and the products are the ingredients of the recipe, but the coefficients tell us about the amounts of those ingredients. Right? So the coefficients of the equation are really, really important when we're talking about the amount of those different reactants and products. Okay? Good? All right. This is the sheet that I gave you on Friday. So Hannah, you noticed that the sheet from today and the sheet from Friday look very similar. Okay? And the sheet from tomorrow will look similar as well. So up at the top it says Introductory to Stoichiometry Problems, and then this one says mole-mole relationships. So start with the one that says mole-mole relationships. Okay? Question number 3 talks about a specific decomposition reaction. So question number 3 from that sheet says potassium chlorate, but it gave you the formula right here, will decompose when heated into oxygen gas, will decompose when heated into oxygen gas and potassium chloride. So here's the reaction, or here's the equation that represents that decomposition reaction, right? We start off with one kind of big compound, and it breaks into smaller parts, okay? It says we can use this reaction to produce oxygen gas for laboratory experiments. So if we need to have pure oxygen gas as a reaction for another reaction, like maybe one of these combustion reactions, this is a way that we can produce oxygen gas. Okay? It says how many moles of potassium chlorate are needed to produce 15 moles of oxygen gas. On Friday, we started talking about a procedure for how to handle this, right? It's asking us about amounts of products and reactants in this reaction. This is a stoichiometry problem. So, where should we start? What's the first step? What's the first thing we should do when addressing this problem? Is that good? I'd say something even before we balance the equation. That's the next step, but let's go with even before that. Kareem, ask the question. What is this problem asking us for? How many moles of potassium chlorate, right? That's the question that this problem is asking us, right? So, how many moles of potassium chlorate? Not really, it's just another letter you have to write. That's fine if you want to. I'm not going to, but you can if you would like.
It's not wrong?
No. Okay. All right, Zach, next thing we can do, right, is what? Balance the equation, right? That's one piece of information that we can use to help us. So I'm just going to rewrite this here so I have a little more room to write some coefficients. Okay? Now, hopefully we start seeing things a little more quickly as we do this more and more, okay? First, is this equation balanced as it is currently written? Not, right? Potassium's looking pretty good, chlorine's looking pretty good, but oxygen's not, okay? Now, we can go through the process, but let's see if we can start like making some connections and some shortcuts. There are 3 oxygens over in the reactants, but there's only 2 over here. So we have this like 3-2 relationship, which we've come across before, right? What's the smallest number that we can get to by counting by 3s and 2s? 6, right? So, in order to get to 6 oxygens in the reactants, I'm going to have to put a 2 coefficient out in front there, right? In order to get to 6 oxygens in the products, I'm going to have to put that 3 there. But by putting my 2 coefficient in front of potassium chlorate, that increases the amount of potassium and chlorine. But luckily, they're together over here, so we put that there. Good? Okay. So now we know what we're looking for. We have a balanced equation, which we said is kind of like a recipe to make what we need to make, right? And then there's one more thing that they told us in this problem. What other piece of information did they give us here? True. That's here. What else did they tell us? We want to produce 15 moles of oxygen gas. So that's a value that we know we're going to have to end up with. So I'm going to start with 15 moles of O2 over here on the left-hand side. Okay? All right. Stoichiometry problems are conversion problems. Conversion problems get rid of units that we don't want and leave us with units that we do want. Conversion factor, time sign fraction bar. Okay? If you want, you can put your original number over 1 just to make the math a little easier, right? But when we're setting up our conversion factor, we said we want to start with units. What unit has to go on the bottom of this conversion factor? Moles of oxygen, moles of O2, right? Formulas are important when we're doing stoichiometry problems because we're comparing different parts of the equation, right? So we got moles of O2 on the bottom. Conversion factors get rid of bad units and give us units that we want, right? So what unit should we have on the top of this conversion factor? Moles of potassium chlorate, right? So moles KClO3. Okay? Good? Yes. All right. This conversion factor is a special conversion factor because it compares one part of the reaction to the other part of the reaction, right? We call this special conversion factor the mole ratio. Okay? I didn't introduce that term to you guys on Friday because we were rolling, but we call this conversion factor the mole ratio. Conversion factors have units, but they also have values that allow us to compare one to the other. Where do the values for a mole ratio come from? Where do we get the numbers from? The coefficients, right? The coefficients give us the ratio of moles of one part of this reaction to moles of another part of the reaction. Now here, we're actually comparing a product to a reactant, right? We started with how much product we needed, and we're trying to figure out how much reactant we want to start with. That's fine. The coefficients work either way. So, what coefficient am I going to put on the top of this conversion factor? 2 on the top, and then what's going to go on the bottom? 3 on the bottom. Okay? This is our mole ratio that allows us to use the recipe to compare one part of the equation to another part of the equation. Elizabeth, go ahead.
Is it 3 because of the coefficient or because
Come on. There we go.
so it's the first 2 coefficients then?
In this case, yes, because those are the 2 parts of this equation that we're comparing. If it had said, if we produce 15 moles of oxygen gas, but also how much potassium chloride would we produce, we would change the top of this fraction to moles of potassium chloride, which is this one over here. It would still have the same coefficient because that's a 2 and that's a 2, but when we're setting up the mole ratio, we look at the coefficients of the formulas that are involved in this conversion. Okay? All right, good? Okay, so now we do a little math. Okay? Moles of O2 on the top, moles of O2 on the bottom. Those go away. The only unit that's left now in our problem is what?
Moles of KClO3.
KClO3, and that's what we're looking for, right? So now we just run this through our calculator, right? Or if you can do it in your head, that's cool too. end up with 10 moles of KClO3. Okay? One problem here, one thing we have to finish up, okay? How many significant digits in this original measurement that we started with? 2 significant digits. Let's not worry about significant digits in our conversion factors because these aren't measurements. They're just numbers, right? There's no certain or uncertain digits here, right? Meaning if we had 2 significant digits to begin with, how many significant digits should we end up with? 2. Is that 2 the way that it's written? Nope, it's not. Because that 0, no decimal point, isn't significant, right? So in this problem here, we would add the decimal point, but nothing after it, right? 10 period. That's it. 10 period. Right?
That's hard.
Good. Yeah, if we added the 0 after the decimal point, that would make it 3 significant digits, and that's too many. Okay.
How did you multiply the ratios?
Okay. So here, Kate, we'll just do math, right? Yep. So when we have 2 fractions that we're multiplying together, so we're just going to multiply the tops and multiply the bottoms, right? So 15 times 2 to begin with, right? 30. And then we're going to divide it by 1 times 3. So 30 on the top, 3 on the bottom.
Yeah, I was cross multiplying.
Okay, no, don't cross multiply. Because we cross multiply when 2 fractions are equal to each other, right? But these 2 fractions aren't equal to each other, we're multiplying them together. Okay? All right, good?
Yes.
All right, so this is the first type of problem, and I think I kind of mentioned this to you. This is what we call a mole-to-mole relationship, right? It's a one-step problem where the one step is a mole ratio that comes from the coefficients of a balanced equation. Okay?
Okay.
All right. Here is the next type of problem, which is labeled mass-mole relationships. This is from the back side of your outline from Friday. So back side of your outline from Friday. So you'll see that Roman numeral number 3 up at the top says mass-mole calculations. Okay? Yes.
I'll ask you in class.
All right, so the problem at the top says when magnesium burns in air, a combustion reaction produces solid magnesium oxide. You've seen this happen before. We did it in the lab, right? With the bright light. We're also going to do it again on Thursday in a little bit more of a controlled reaction. Okay? So it says, how many grams of magnesium oxide would be produced from 2 moles of magnesium? All right, starting off. What's our first step when we're addressing this problem?
Find out
What are we looking for? So, Elizabeth, what are we looking for in this problem?
how many grams of magnesium oxide would be
How
produced?
many grams of magnesium oxide would be produced, right? So here, we're going to start off with how many grams of magnesium oxide, okay? I didn't give you the equation here, but I will give you the equation on quizzes and tests, okay? And we already, there's a reason why I picked that, because, okay? So here, this is telling you that this is a combustion reaction, right? So that means, what does one of our reactants have to be?
O2.
O2, right? If it's a combustion reaction, that means we have oxygen reacting. What is oxygen reacting with in this problem? Magnesium, right? And it produces magnesium oxide. Okay? Is it balanced the way that it's currently written?
No.
Nope. Pretty, not too hard to balance that one, right? So let's balance it pretty quick. Okay. And there's our balanced equation, okay? All right, so we know what we're looking for. We have one piece of information to help us. What's the other piece of information that we were given in this problem?
2 moles of magnesium.
Okay, we know that we're starting with 2 moles of magnesium. All right, so we'll go here, 2.00 moles of magnesium. Okay, here's where this problem gets a little bit different than what we did before. Okay? So, stoichiometry problems are conversion problems. They get rid of bad units, leave us with good units. Einstein fraction bar. Okay? We can put this over 1 if we want. All right. What unit has to go on the bottom of this conversion factor?
Moles of magnesium.
Moles of magnesium has to go on the bottom here. Okay? Now, if you're writing in pen, stop there. Okay? If you're writing in pencil, you can write the next thing if you want to, because you can erase it, but what I'm about to write on the board isn't the right thing. So let's just talk through it. Okay? So, I'm going to write the wrong thing. W-R-I-T, the W-R-O-N-G.
So wait, but you're
Yes, but I will fix it. Yes, I will.
You're going to write a wrong, so you're doing both.
Yes, I will write the wrong thing, but then I will write the wrong. Whoa, this is like in English. This is like English class here. So, okay, so now, according to the rules we've done up until this point, conversion factors get rid of bad units and leave us with good units. So according to what we've done so far, we should put grams of magnesium oxide up on the top of that conversion factor. But here's the problem, okay? When we put moles out there, we're counting, right? Moles is a number of things. And it doesn't matter what we're counting, we always have the same number of things. Okay? But grams is a weighing thing. Right? Here's the example that I used this morning. Let's say you have a recipe. Okay? I'll use this recipe because I know this recipe kind of by heart because I make this a lot at home. Okay? Pancakes. Okay? So, pancakes. Okay? In order to make pancakes, you start with a cup of flour and you eventually add a cup of milk. Okay? Both of them are a cup, but do they weigh the same? One's denser than the other one, right? Milk's going to be more dense than the flour. So even though we need a cup of both of them, we couldn't say use 16 ounces of flour and 16 ounces of milk, because that's not the same ratio as 1 cup to 1 cup. Okay? We have a conversion factor where we have moles of one of our formulas, but grams of something else. That doesn't work. Okay? We can't have moles of one thing and grams of something else because we're not talking about an even number of things. Okay? So this conversion factor that I wrote up here, this is not how we're going to start this problem. Okay? So I'm about to right the wrong and erase this. Okay. We can compare one part of our equation or reaction to another part of our reaction through the mole ratio. But mole ratios have moles and moles. So I can put moles of magnesium on the bottom, and I can follow that up with moles of magnesium oxide on the top. I can do this. I can have magnesium and magnesium oxide because they're both moles. Okay? This is an okay step. This is what we call, right? This is the mole ratio. Where do our numbers for our mole ratio come from?
Coefficients.
Coefficients, right? So I look up here. Here's magnesium oxide. It has a 2 coefficient in front of it. Here's magnesium. It also has a 2 coefficient in front of it. All right, good? So, now we do a little bit of math, right? Moles of magnesium is on the top of the fraction here. Moles of magnesium is on the bottom of the fraction there. They cancel. But now, what unit do we have left? We have magnesium oxide, but what unit of magnesium oxide? Moles of magnesium oxide. What did this question want us to give, or what does it want us to find out? Grams of magnesium oxide. Okay? So, we have done a conversion factor, but we still don't have the units that we want. So this one-step problem now becomes a two-step problem. Okay? What unit has to go on the bottom of this second conversion factor?
Moles of magnesium oxide.
Moles of magnesium oxide has to go on the bottom of this second conversion factor because we're trying to get rid of moles of magnesium oxide. Then, in an ideal world, what unit should go on the top of this conversion factor? Grams of magnesium oxide.
By weight.
Okay. So we have moles and grams in the same conversion factor again. But what's different about this moles and grams than the one that we wrote incorrectly before? They're the same formula, right? So, this conversion factor is an old friend,
Molar mass.
the molar mass.
Oh my gosh, how did I not see
Okay.
it before?
All right. Where does the molar mass come from, or where do we find the molar mass?
Periodic table.
On the periodic table, right? Now, here's something that we have to keep in mind. Okay, well, two things we have to keep in mind. First, this is a molar mass. Even though in our balanced equation we have a 2 coefficient in front of magnesium oxide, when we're talking about the molar mass, how many moles are we talking about? Just one, right? So even though we had a 2 coefficient in front of molar mass, in front of magnesium oxide here in the mole ratio, when we're using the molar mass, we're only going to put a 1 there. Always, always,
Can I
always.
guess it's on the top?
Coefficients only show up in the mole ratio. When we're using molar mass, we only have on 1 mole, okay? Hannah, what's going to go on the top?
6.02.
Nope.
No?
Nope. Okay. Not 6.022 times 10 to the 23rd. So, when we get the molar mass, we said we go to the periodic table, okay? So over here, right, for our purposes, before, when we were doing all of our conversions, we were only doing them for a single element. So the molar mass of magnesium is 24.305. But do we only have magnesium in this problem here? No, we have magnesium joined together with oxygen. So what do you think you're going to have to do to find the molar mass? You're going to add the molar mass of magnesium plus the molar mass of oxygen. Okay? So add the two of them together, and that will be the number on the top.
40.3.
Is that what it is?
Yeah.
40.305?
0.304.
0.304 because the oxygen is 1 less. Sorry.
Accident. You're right or you're wrong.
Say
I'm
again?
stating a fact. He's just
All right, so now, right, now, moles of magnesium oxide cancels there. Moles of magnesium oxide cancels there. What's the only unit that we have left in all of these conversion factors? Grams of magnesium oxide. And that's good because that's what we want. So now we do a little math, okay? I don't care if you like see some shortcuts that you can take, that's cool, right? However you get to the final answer is fine with me, right? For instance, in this conversion factor, the mole ratio, the one circled in yellow, we have 2 on the top and 2 on the bottom. So what are those two 2's doing to each other?
Canceling each other out.
So we can just kind of forget about this whole middle section if we want to, right? And then we can just multiply this times this.
It's 80.608.
Okay. So when we multiply it all out, we end up with 80.608 grams of magnesium oxide.
Or 80.60.
I got 608.
I got 6 because you have to have significant digits.
Oh, right, significant.
So, how many significant digits here?
Great.
So we should round our answer to
80.6.
80.6.
Oh.
So close, yet so far away.
All right. Are we good with the 2-step problem?
Yes, are we learning 3 steps?
Not today.
So for the mole ratio,
Yep. Hey, questions? Hold on.
Answers.
why can't we just use
Okay. In this case here, we can compare moles of one thing to moles of another thing because, so Elizabeth, in this case, we know we need 2 magnesiums for every 2 magnesium oxides. That's what this says. Okay? That doesn't mean, individually magnesium weighs differently than magnesium oxide. So we can't say that this is 2 grams and 2 grams because they're different from each other, right? That's why we can compare moles to moles because it's always the same number of things. But then, if we want to find out an actual mass value, we've figured out how many moles of magnesium oxide we would need or produce, but we have to use the molar mass to turn that into a value that we can like put on the balance or something like that, right? We can't really weigh a mole of something, right? Or we don't have it, right? It's just an amount. It's a counting thing. But this turns it into an actual weighing thing.
theoretically then we can use the mole?
Yes, we can always compare moles to moles. And we can compare grams to moles as long as we're talking about the same formula. But you can't do moles of one thing and grams of another thing. Okay? All right, here's what I want to do before we take off. Okay? So, the sheet that I gave you today, that has a bunch of problems on it. Here's number 4. There's a reason why I wanted to do this, okay? So I'm going to, we're not going to have enough time to run through the whole problem, but I'm going to at least set up the conversion factors for you so you can practice this a little bit more on your own, okay? All right, starting off. How many moles of NO are formed? So this problem starts, not that way. Okay, how many moles of NO? Okay, balanced chemical equation. Okay, balancing this one is a little tricky, so I'm going to run through it pretty quickly, all right? So, we're good on nitrogen. Hydrogen, not so good. 3 hydrogens in the reactants, 2 hydrogens in the products. There's that 3-2 thing again, right? So I'm going to put a 2 out here and a 3 out here to get me to 6 hydrogens in the reactants, 6 hydrogens in the products. Okay? Here's where we run into a problem that I'm going to tell you how to fix. Okay? Oh, sorry, one other thing. Here, right, by putting this 2 coefficient in front of this number, I'm going to have to put that 2 out there, right? Okay? Here's where we run into this problem. 5 total oxygens in the product. Yes?
Yes.
But oxygen only comes in groups of 2 over in the reactants. We can't get to 5 with groups of 2. right? We have an odd number over here and an even number over here. So here's how we can fix this. Sometimes we run into this when we're balancing equations. Let's just double everything, okay? So this 2 is going to go from 2 to 4. This is going to go from 2 to 4. And this is going to go from 3 to 6.
Is that better?
Well, now how many oxygens do we have over in the product? 10. And that comes in groups of 2.
Oh, yeah.
So we can go there.
It'll work
Okay?
out.
All right. Okay. There's my conversion factors set up with units. Okay? Hopefully from that, on your own, you can figure out what numbers need to go in all those different places, okay? I posted answers to this problem and all the other problems from that sheet on the calendar, so you can check them out tonight if you need to, all right? Practice, practice, practice. It's the only way we get better.
Mr. Flansek, is a polynomial an equation?